In section 3.2, we're going to discuss polynomial functions and their graphs. To start off, let's talk about the definition of a polynomial function. It says let n be a non-negative integer and let this series of values an minus 1 all the way down to a2, a1, and a0 be real numbers where an is not equal to 0. The function defined by f of x equals an x to the n plus an minus 1 x to the n minus 1 plus and so on to a2 x squared a1 x plus a0 is called a polynomial of degree n. The number an, which is the coefficient of the variable with the highest power, is called the leading coefficient, which we're going to abbreviate LC. Now there's a lot to this definition, but there's really only a few things we really need to point out here. For instance, in the front, we'll have x raised to the n power, which they're referring to here as the largest power. And again, we're calling that the degree. It should be the one in front if we order it from largest power and in descending order of power. The number in front of that, the coefficient to the largest degree term, is called the leading coefficient, which again, for convenience sake, I'm going to abbreviate that LC. So if you look at this polynomial here, for example, f of x equals negative 2x to the 6th plus x to the 5th minus 5x to the 4th plus 2x to the 3rd plus 8x squared plus 9. This would be a polynomial function where we put the leading coefficient in front. That would be the negative 2 in this case. The leading coefficient is negative 2. The degree of this polynomial, again, is the biggest power. So the degree in this case would be the 6. And so when we start looking at polynomial functions, we're going to have this setup basically where the powers are kind of like counting numbers. The powers like 6, 5, 4, 3, 2, 1, and so forth. Polynomial functions as a result will not have any of the following. Negative exponents will not show up in a polynomial function. Fraction exponents will not also show up there. So if we see a negative exponent or a fraction exponent, we can automatically say it's not a polynomial function. As a result of the first two, that would also mean that we're not going to see any roots with x inside, any square roots, cube roots, anything like that. Also, we're not going to see any kind of fraction with x in the denominator. So those four things are things we're going to be looking out to determine if we're looking at a polynomial function or something that's different than that. Now, on the other hand, you can still have fractions as coefficients, like 1/2 x to the 3rd. You're just not going to see those fractions in the exponent, and you're not going to see x underneath in the denominator. So with that in mind, let's look at these examples. Which are polynomials and which are not? Looking at the first one, f of x is equal to 5x squared plus 6x. There are no negative powers, there are no fraction exponents, no roots or other kind of fractions with x in the denominator. So this one checks out as a polynomial function. If we look at the next one, g of x equals 7x to the 5th minus pi x to the 3rd plus 1/5 x. Now there are fractions, but again, they're coefficient fractions, not fraction exponents. All the exponents here are powers like the 5th power, the 3rd power, and technically an understood 1st power at the end. Those all match the description of a polynomial function. So that one checks out, and we'll say that one's a polynomial function also. On the other hand, if we look at the next one, h of x equals x to the 1/3 power minus 4x squared plus 7. This one has a fraction exponent. So that's automatically going to mean it's not a polynomial function. The next one also has a square root x, meaning that it's not a polynomial function. The next one also, you notice that there's an x to the 3rd in the denominator, which means that it's not a polynomial function. The next function, which says r of x is equal to 10, that one is a polynomial function. Even though you don't see x there, technically you could think of it as x to the 0 power as a placeholder for x. So it's like 10 or just 10x to the 0 power. Either way, it's the same. But in either way, it matches the description of a polynomial function. The last one, n of x equals 2 parentheses x minus 7 to the second power, parentheses x squared minus 3 all raised to the third power. This one is a polynomial function. None of the powers are negative or fraction exponents, and there's no square roots or fractions with x in the denominator, so it checks out. For the ones that we identified as polynomial functions, let's discuss their degree and their leading coefficient. In the first case, at 5x squared plus 6x has degree 2 and a leading coefficient of 5. On the next one, we notice the largest power is equal to 5, so degree is 5, and leading coefficient is 7. For the function that's simply a constant, that would be considered as degree 0, and leading coefficient is just the number itself equal to 10. The last one is still a polynomial function, but the thing about this one is it's factored. So we can't just look at it and tell what the highest power of x is, because the powers of x have been factored apart into separate factors. So in order to know what the highest power of x is, let's consider that the first factor has an x squared from the power of 2 up here. This other factor, though, has a power of 2 raised to the third power. It would be like x squared raised to the third power. And these two factors are multiplied together. Now what happens in the case of a power raised to a power is those powers multiply together. So we're going to have an x squared from the first term times an x to the 6th from the second term. When you have two terms which are multiplied together, their powers add. So to the second power and the 6th power becomes to the 2 plus 6 power, or 8 power. What that means for us is that the degree becomes 8. So we have to consider that those factors are multiplied, and therefore we have to put the powers all together to know what the biggest power of x is for the degree. Now the leading coefficient is still going to be just the number that sits out here in front. That's still going to be the leading coefficient. So leading coefficient on this one is 2. When we discuss the graphs of polynomial functions, we'll talk about how they're going to be smooth and continuous, meaning there are no breaks, gaps, or sharp edges in the graphs of a polynomial function. So of the three that you see here, this one here, the second graph, has a sharp edge to it. So that one is not going to be a polynomial function. Graphs 3 and 4 have a break or a hole in the graph. There's a break here on this one, and there's a hole on this one. So neither of those are polynomial functions. However, the first graph is smooth and continuous. So whatever the graph is that goes with it, or whatever function goes with it, will be a polynomial function. The next thing to talk about for polynomial functions are the so-called zeros of a polynomial function. Now, the zeros sometimes are referred to as roots of a function or an equation. That basically means the values of x where the function is 0. In other words, we solve for x to make f of x equal to 0. Those values of x are referred to as the zeros of the function. Another big takeaway of this is exactly the same as where the x-intercepts are located. So talking about x-intercepts, zeros, roots are all kind of the same thing ultimately. We go about solving for them basically in the same way. A particular feature of zeros on a polynomial function is their so-called multiplicity. If you have a factor of x minus r and it occurs as a factor k times, then we say it's a zero of multiplicity k. For example, if you had a factor in your polynomial function like x minus 2 raised to the fourth power, then the multiplicity is called 4 here. That's going to describe that particular number that goes along with that factor. Why we even discuss multiplicities is because it tells us about the x-intercepts, and if the graph touches and turns, or if it crosses. If it's an even multiplicity, then it touches and turns. If it's an odd multiplicity, then it crosses. So what that's going to look like for us when we start drawing graphs of polynomial functions is we could have them come up and do a few different curves up and down before heading one way or the other. Crosses is like it says, it goes through and crosses all the way through the x-axis at the x-intercept. However, touch and turn is where it doesn't go through. I'm going to abbreviate that t plus t for touch and turn. It just touches the axis, turns, and goes the other way. Let's go through an example of determining first off the x-intercepts and everything else like the multiplicity, cross versus touch and turn. So this one's already factored for us. X squared, x plus 1 in parentheses to the third, x minus 2 in parentheses to the fourth, x minus 3 in parentheses. To find the x-intercepts, we set y, or f of x, equal to 0. So we set this whole thing equal to 0. And to solve, when it's been factored, we take each factor and set it equal to 0. So the x squared, the x plus 1, the x minus 2, the x minus 3, each equal to 0. Notice that I'm just taking what's inside the parentheses, not the powers themselves along with it. Just what's inside the parentheses set equal to 0. For the first factor, x squared, that's really just going to mean x itself is equal to 0. For the plus 1, I'm going to subtract 1 over to get x is equal to negative 1. For minus 2, I'm going to add the 2 over to get x is equal to 2. And finally, for the negative 3, I'm going to add the 3 over to get x is equal to positive 3. Okay, so those are the x-intercepts. Now to go along with each of those is the multiplicity numbers, which we're going to find by looking at the powers above each factor. So all these numbers up here are the multiplicities. So for instance, for x equals 0, we started from x squared, that has multiplicity 2. For negative 1, if we check the factor, we have multiplicity 3, multiplicity 4, and multiplicity 1. So let's scroll down here and look at what all we have here. We have 0 with multiplicity 2, negative 1 with multiplicity 3, 2 with multiplicity 4, and 3 with multiplicity 1. We look at these multiplicity numbers to see, are they even or are they odd multiplicities? First one says multiplicity is 2, which is an even number. Even number means that it touches and turns. Multiplicity 3 is an odd number. Odd multiplicity means that it crosses. 4 is even, so that means it touches and turns. 1 is odd, so that means that it's going to cross.